All right. I'll turn mine off as well. How would you like it if I told you that this is the halfway point of the semester? We're halfway through it. Some of you are like, yay, and some of you are like, only halfway? Like, are you serious? We have to go through more of this? 8 o'clock in the morning stuff? All right. I'm a lecture or two behind on the attendance. I'll admit my goal is to have that updated by the end of the week. I want to talk to you a little bit, though, about logistics moving forward, because surprisingly enough, at least for this class, we don't have a great amount of time between now and spring break, because we only meet 2 days a week, right? So I thought it would be a good idea to give you a little bit of a taste of things to come. So today, what we're going to do, last lecture and this lecture are intended to sort of catch us up, if you will, from the delays that we had as a result of the weather. What we're going to do today is we're going to continue our review of the important statics concepts, if you will, from last semester. So last time we discussed centroids and moments of inertia, and today we're discussing shear and moment diagrams. And I want to tell you why we're doing all of this. If you remember, I said that a good chunk of this class is all about deriving the big four stress formulas, if you will, right? Axial, torsion, bending, and shear. And the stress formula for bending is this. Okay? This is sort of what we're after. And this is sort of what we're talking about indirectly right now. Okay? Because our last lecture, the whole focus was I, the moment of inertia, right? Now this term y is the distance from the centroid to the point in question. So the last lecture sort of served to review that too. Okay? But there's something else there, and that's m. And what is m? That's bending moment. And where does bending moment come from? Well, it's the internal moment that a given element or member is subjected to. And where do we get that? We get it from the moment diagram, right? So it obviously would make sense that you need to be able to construct shear and moment diagrams in order to effectively assess bending stresses. And since that was a long time ago, November seems like ages ago in a different course, in a different semester, it's probably a good idea to have a little bit of a crash review of shear and moment diagrams. So when we come back next week, Tuesday and Thursday are going to be our main focus. Our main focus is going to be bending stresses. What we're going to do is the first lecture on March 1st is going to focus on bending stresses in what I would call homogeneous beams, beams of one material. And then we'll look at composite beams, which are beams of two materials. Because the elastic bending theory that we utilize to determine bending stresses is limited to beams of one material. However, that doesn't mean we don't build beams of two materials. So we have to be able to modify that accordingly. What we're going to do the following week is we're going to do our last stress formula, which is transverse shear stress. It doesn't take a lot of work, if you will. So we can do that in a single lecture. And then right before spring break, we're going to do our intro to beam deflections, because beam deflections are another animal in and of themselves. We got a little bit of calculus we got to integrate to that, etc. Then margaritas and mai tais. All right. When you come back, we're going to have our exam review, and then we're going to celebrate on Thursday. So we're not going to have an exam on Tuesday when you come back, but we are going to have one on Thursday. Okay. Sound like a plan? I am going to assign a homework on beam deflections, but it's not going to be due until the Thursday after exam 2, so you got plenty of time on it. I'm not going to, it's not going to be appreciably longer, but I just want you to have it so you can chip away at it, but I'm not going to make it due until well after the exam. Because after the exam, we're going to go back to beam deflections, because I'm sure there's going to be like a, wait, what were we talking about? Kind of aspect to it. So, make sense? Okay, let's talk about shear and moment diagrams. I did one thing I forgot my clicker, so I have to go back and forth to the keyboard. Okay, so a lot of these lecture notes actually came from last semester. I sort of took what we talked about last semester and I kind of cramped it into a single presentation because it's sort of a review. Shear and moment diagrams, they are incredibly powerful tools, incredibly useful tools for engineers. There are things that when an engineering student graduates with a degree, there are certain skills that we just sort of expect them to be able to do. You know, if you're a mechanical engineer, you know, understanding the laws of thermodynamics or understanding how to manipulate Bernoulli's equation or whatnot. And civil engineers, mechanical engineers, even you biomedicals in the room, the construction of a shear and moment diagram is one of the most seminal tasks that engineers are asked to be able to perform it. It's just sort of an engineer's bread and butter, if you will. Now, the reason why they're so important is because they graphically display the internal responses inside of a given beam or a given frame, and you need that in order to design. So for example, when we're using sigma equals my over I, the m comes from the moment diagram. And so if I was designing this beam, I would design it for a moment, maybe of 460 foot-kips, right? So that's the moment, and I wouldn't know that if I didn't construct the shear and moment diagram. So it's incredibly powerful, incredibly useful for design. We're also, the transverse shear stress stuff we're talking about in a couple weeks, we get the transverse shear from this as well, so we might use 46 kips for our transverse shear. Okay, so let's go back to statics. So remember, if I'm sitting on the table and somebody breaks out the samurai sword or a lightsaber, if they happen to be a sci-fi fan, if I'm sitting over here and they cut through the table, I am going to fall on the ground. Their grade in the course is going to be damaged as a result, right? Okay. The reason is that because inside the table, right here, there are internal responses that are keeping the table upright. So analytically, we use the tool of cutting a section to investigate what are the internal responses inside that section. And so some of this stuff we've already dealt with. So for example, if there's an internal axial load P, we now know what to do with that. We can take that axial load P, divide it by the area to get an internal axial stress. And then we can compare that axial stress against sigma allowable, factors of safety, etc., to see whether or not the member is too stressed. What we're now going to do is see what happens when we look at the internal moments and the internal shears as well. Now our goal is to plot the shears and moments across the section. The problem with just cutting a section at various points is they will give you the internal shear and moments. That's not to say they won't do that, but they'll only give you the internal shears and moments at a particular point. But that's great for spot checking. But what if I want the internal shears and moments everywhere? What if I want the shear and moment response across the length of the structure? What that basically means is plotting the shears and moments or graphing the shears and moments along the beam. That's what a shear and moment diagram is. All it is just a graph of the shears and moments along a given element. And what we do in order to do that is we develop a more intuitive graphical approach. We have a little bit of a calculus basis behind it. If you remember from statics, what is arguably most important when you're assessing or trying to construct a shear and moment diagram is that you understand that polynomial relationship as it pertains to derivatives and integrals, right? So if you have a line and you integrate it, you get a parabola, right? You take a parabola, you integrate it, you get a cubic function, etc. And those integral derivative relationships are critical in order to develop a means of constructing shear and moment diagrams. Now the way that works from a derivation perspective is we look at our beam, and again, a lot of this stuff came from notes from last semester, so hopefully for those of you that had me from statics last semester, this is familiar. You remember seeing this in that big old Smith Hall 154 atrium style room that we were in. So what we do in order to derive this approach is we say, all right, I've got this beam that has these weird variable loads on it. What I'm going to do is I'm going to slice out a little element. Okay, and we're going to say that element is dxy. And if you remember from calculus, dx is just a differential length along the x-axis that's really, 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 really tiny, right? We start off in calculus by calling those delta x's. and then we take the limit as those approaches 0, so we have this infinitesimal small element dx. And so what I propose is that from one side of the element to the other, so for example, if I look at the moments, I have a moment on the left side, and on the right side, I have a moment plus some increment. I don't know what that increment is yet. We're going to figure that out. Same thing with the shears. I have some shear V and some shear plus some dV increment on the right side. Now, a couple things that's worth mentioning. If you notice, I have the shears drawn in equal and opposite direction, the moment in equal and opposite direction. Those are drawn according to our accepted sign convention for internal shears and moments. The other thing that's worth mentioning is the load. So on the original structure, the load is variable, right? It's going all over the place because the idea is that we just want this to represent some arbitrary load function across the structure. But if I'm looking at some infinitesimal element that's like dx wide, that's so tiny that across that really narrowly or really thin element, I could just assume the load is uniform, okay? And so once I have that, I can say, all right, I remember those old equations of statics. I have the sum of forces in the y direction and the sum of moments equals 0. So when I look at the sum of moments in the y direction, I say, all right, what do I have going up and what do I have going down? I got v going up. I've got this going up, which is w times dx. And in terms of what's going down, I've got this, v plus dv. And all I do is I cancel out all of the terms that are repetitive, solve, and I get this, dv equals w dx. By the way, just a heads up, I'm not going to make everybody derive this like on an exam or anything. I don't want you to think like, oh, I have to repeat this. You're not going to have to do that. I just want you to remember this stuff throughout the examples that we do. And by the way, again, these notes are also on Blackboard, so if you miss something, don't worry, they're on there as well. Now, when we sum moments on the right side, this, what I'm doing, I'm taking moments in this direction as positive. So what do I have? I have a negative m. I don't consider this, I'm summing moments on the right. So I have negative m. I have v dx. I don't consider moment from this this force right here because it's going through the right side. I have the m dm over here. But in terms of this load here, what's the moment contribution? Well, it's the force, w dx, times the moment arm. And the moment arm is dx over 2, because that's like a distributed load. Remember, with distributed loads, we can idealize that as a point load acting through the centroid. With me so far? Okay. Well, when we start carrying out our algebra, we get this term here, this w dx squared over 2. Dx is a really tiny number. What happens when you take a really tiny number and you square it? You get a really tiny number. So those higher order terms, we can just neglect those because they're basically going to be 0. Solve it out, and we get this. Now, what this should look like to you is basic calculus relationships. And I can rearrange those a little bit and get this. So I propose that if I have, let's say, the moment diagram, and I differentiate that, I get the shear diagram. If I take the shear diagram and differentiate that, I get the original loads on the structure. That's fine, but that's not really what we need. See, it's fine if we're given the moment diagram and the shear diagram, we can differentiate those to get the loads. But typically it works backwards. Typically we've been given the beam, here's the loads on the beam, and we need to determine the shears and moments. So if differentiation will take us from moment to shear to load, then integration will take us from load to shear to moment. So what we have to do is, in order to construct our shear diagram, we need to integrate the loads. And in order to construct the moment diagram, we need to integrate the shear diagram. Now, so I'm sure as I'm saying this, you're thinking, oh God, Calc 2 all over again. Oh no. The benefit of the types of problems that we're dealing with is as follows. Now, I would argue that if you have a really funky load scenario, if you have a really like wavy load or some sinusoidal load on a beam, well then, yes, you are going to have to break out the calculus to construct a shear and moment diagram. But we don't deal with that in the real world in engineering. We just don't. We deal with beams that have concentrated loads, distributed loads. Every now and then we have a triangular load and whatnot, but I mean, for the vast majority of applications in real world engineering, we just don't. We deal with simple loads. And because we have an inherent understanding of the derivative and integral relationship with polynomials, we can develop a graphical means of constructing shear moment diagrams and sort of avoid the calculus altogether. Okay? So let me explain. All right? So first off, again, man, you can tell I definitely stole these notes from statics, because I say we'll discuss this during the next lecture. No, we're discussing it right now. But the key aspects of understanding what's going on in the construction of shear and moment diagrams is, again, this. So for instance, if I have, let's say, a cubic function, and I take the derivative, I'm going to get some sort of quadratic function, right? Like x to the third. What's the derivative of x to the third?
3x squared.
There you go. So if I take a cubic function and I differentiate it, I get a parabola, right? A quadratic function. Because 3x squared, that's a parabola, right? Now what happens if I take 3x squared and I differentiate that? What's the derivative of 3x squared? 6x. What does the graph of 6x look like? It's a line, right? What's the derivative of 6x? 6, right? What's the graph of that look like? It's a constant, right? So from a derivative perspective, if I go from cubic to quadratic to linear to constant, that just follows the polynomial differentiation rules that we learned all the way back in Calc 1. Well, what we're trying to do is work backwards. We're trying to go from load to shear to moment. So we're going to be working this way. So we're going to be integrating. So as long as you understand those patterns, that's really all you need. For our graphical approach, what we can do is we can utilize our derivative and integral relationships to make some pretty straightforward conclusions. So the first thing we're going to have to do is we're going to have to construct a shear diagram. So between load and shear, what we know is, number one, we know that the slope of the shear diagram is equal to the load. That comes from this, right? What does the derivative of shear equal? It's the load. But what does the derivative give you? It gives you the slope of the function, right? So we know that that at a given point, whatever the slope of the shear diagram is, that equals the load, and the change in shear between 2 points is equal to the magnitude of load between these 2 points. That just comes from integration. Between shear and moment, sort of the same thing. The slope of the moment diagram is equal to whatever is reported on the shear diagram. And between 2 points, the change in moment is equal to the area under the shear diagram. Now let me pull up some images here that are probably a little bit familiar, maybe a little bit more visceral. So we start off our graphical approach when we did this in statics. We started off with concentrated loads, right? And remember how it works. So the first thing you did is you computed your support reactions, right? And then you say, okay, I've got my support reactions. I need to start drawing the shear and moment diagram. How did you treat the point loads? The point loads were just jumps on the shear diagram, right? So if you had a beam and the only thing it had on it was point loads, the shear diagram kind of looked like a stair step, right? You would maybe jump up your reaction and then when you get to the very end, you have some reaction that brings you back up to zero, right? So from a calculus perspective, so what do we have here on the shear diagram? Here and here, we have no load. Like, there's no load here, and there's no load here. So there's no slope here, no slope there. What is the slope of a horizontal line? It's zero, right? So that's why the shear diagram looks like stair steps when all you have is concentrated loads, right? Now you do have value on the shear diagram, you just don't have any slope. Now, what's the integral of a constant? It's a line, a linear function. So constant shear, linear moment. Constant shear, linear moment. What is the slope of this line? Whatever that shear is. What is the slope of this line? Whatever that shear is. Just bringing it back, y'all remember this? Any questions on this? Now, that's for concentrated loads. What about distributed loads? Well, for distributed loads, first off, and probably the most common mistake students make when they first start constructing shear and moment diagrams is this. So, whenever we're computing support reactions, a common tool that we will use is to take distributed loads and turn them into point loads. Makes them a little easier to deal with in terms of computing support reactions. That's fine for static equivalency for the means of computing support reactions. It is not fine for constructing shear and moment diagrams. We have to revert back to the original loading. And that's got to make sense if you just think about what we're talking about. If we're trying to plot the shear and moment diagrams, which, again, are the internal response inside a beam. I mean, wouldn't that response change depending upon the manner in which you apply the load? For example, here's a table. I got 200 pounds in my hand. What's worse, putting 200 pounds right in the middle or spreading it out? Obviously, lumping all that load right in the middle is going to be a little bit harder on the table than it is spreading it out, right? You got to convert back to the original loads in order to properly construct the shear and moment diagrams. Does that make sense? You will over-predict moment and whatnot if you do not revert back. Now, what does it look like when you construct a shear and moment diagram for a distributed load? Well, remember that whole lot to a little thing we discussed in statics? So I know that when we brought that up, there was like, what is this lot to a little thing? So, if you have a constant load, that means you're going to have a linear shear diagram. The slope of the shear diagram is going to equal whatever that load is. Okay? So you're going to go from, let's say, a high shear to a low shear, a lot of shear to a little shear. What that means when you construct your moment diagram is you have a lot of slope to a little slope. So a shear diagram in this fashion is going to result in a parabola that goes like that. Now, if I were to keep plotting that parabola would open down, right? Does that make sense from a math perspective? The second derivative would be negative, right? Remember that whole concavity test, second derivative, negative, opens down like that? Man, bringing back all that Calc 1, Calc 2 stuff, right? You're like, it is 8 o'clock in the morning. We haven't yet finished our coffee. Why are you doing this? Okay. Before we jump into some examples, just a quick refresher on support conditions to make sure that everybody is familiar with that. If you remember in statics, you open up the textbook and there's like tons of those things, right? There's like, the roller that only has, or the roller along the track that has like reactions this way, and then a moment that way, and all these weird contraptions. In real world practical engineering design, more often than not, we tend to use some pretty straightforward boundary conditions. The most common 3 boundary conditions are, first off, the pin support. The pin support restricts motion in the X and Y direction, but it allows rotation. And one thing I will say, when I say, this is what we see in the real world, keep in mind that what we are doing whenever we analyze these systems is we're not analyzing the structures more than we are the mathematical models that represent structures. And I'm saying that these 3 boundary conditions are the most common boundary condition elements that we use in our analytical models in practical engineering design. So we have our pin support, which is contains reactions in the X and Y direction. We have our roller support, which only restricts motion in the direction of the roller, and that reaction could be up or down, just only one of them, only in the direction of the roller. And then we have our fixed support. Our fixed support basically encases the beam or affixes both the shear and moment transferal to the next adjacent element. So we have 3 unknown reactions, x, y, and moment. Okay, I've done a lot of talking. You want to do some problems? Let's do some problems. So just so you are aware, we've got 2 problems we're going to do, this one and this one. One's a cantilever beam, one's, it's not simply supported because the supports aren't at the end. So there's a lot going on here. But I really like this problem because there's a lot going on with distributed loads and point loads, and it's a really, really great review. And again, this is one of those instances where I believe that this is way harder than what's on the homework assignment and whatnot. All right, let me pull this up. So I have this here. By the way, I also have an image of the beam down here. I'm going to refer to that later. So I'll give everybody a sec to sort of draw this out. And we will get to work. Hopefully everybody brought their Casio FX115ES Plus or similar scientific calculator. You would have thought I rehearsed that. On a side note, I do wish the weather would make up its mind. It could be warm or it could be cold. I'd be fine with either. Pick a lane. I think because when it changes so much, I think that I perceive it to be colder than it really is. Because it's actually not that cold, but I feel it's like freezing outside. Because it was, you know, the other day it was in the 60s, close to 70s. Yeah, that makes sense. How many of you, I'm just curious, how many of you all still feel comfortable with Shear moment diagrams? Or is that like, oh goodness. What's that? Well, that's what we're doing today. I can't even be bothered to change some of the text in some of the slides, apparently. My apologies for that. Okay, everybody good? Okay, so a couple of things. We've got a point load, we've got distributed loads. Let's deal with our reactions first. How many unknown reactions are here at B? What type of support is that? Now, before we move on, what can you tell me about one of those reactions? There we go. Because if I sum forces in the x direction, there are no forces laterally on this system. By the way, when you first start looking at shear and moment diagrams, that's usually pretty common, and they're usually pretty easy to assess. Now, that's not to say that flexural elements don't also experience axial load in the real world. That is incredibly common. For example, if you look at building design, we do not design the entire building to withstand lateral load. Let me give you an example. When you are in a car with your friend and they're driving and they don't know what they're doing, they're going 55 miles per hour and they hit the brakes, what's the first thing that you hit? What? Dashboard? So nobody's hitting their seatbelt? Because you're wearing it, right?
Sure, yeah. Right.
Oh, now that I bring up the seatbelt, now that you're wearing, oh, okay. We hit the pavement, we hit the glass. The point I'm making is that we don't design the entire car to hold a passenger back in the event of a collision. We install a specific system inside that car. We call that system a seatbelt, right? It's not the whole car holding you back, it's a specific system. We do not design entire buildings to withstand wind and lateral forces. Instead, we install a given system. So for example, it's not all the beams and columns in the building, it's select beams and columns. And for some of those beams and columns, not only are they experiencing flexing, from lateral forces, but they're also experiencing the weight of the building. So they experience both axial load and bending. So we have elements subjected to multiple stresses and combined stresses. We will talk about how a means of dealing with combined stresses later on this semester. So, like we do each of the 4 big ones, and then what happens if you have all of them acting all at once. Okay, that was enough of a tangent. We have a roller here, so we have a reaction right there. So 3 reactions, 3 equations of equilibrium. Now, what I'm going to do is I'm going to take this distributed load and I'm going to collapse that into a single point load. Well, how many feet is it acting over? So that's 4 and 6 is 10, 6 is 16. So I have 400 pounds per foot over a distance of 16 feet. What's 400 times 16? 6,400? Did I do that right? So I need to collapse that into a load of 6,400 pounds, and how far over from A am I going to place that? So here's what I'm getting at. I've got a 6,400 pound load, which represents this distributed load. What's this dimension? There we go. Does that make sense? I feel like I'm doing that kind of quickly and everybody's like not following along. If you're not getting what I'm doing, let me know. Everybody good? Okay. So help me out. If I want to determine these support reactions, somebody tell me what should I do? Bringing it back to Engineering 213 land. If I sum forces in the y direction, would that yield one of my reactions right off the bat? No. I would know that By and Cy have to add up to equal whatever this downward load is, but it wouldn't tell me what each of them are. So if I can't use sum of forces in the y direction, what's my other equation of equilibrium? Sum of moments. And where should I sum moments in general? Well, in general, I should sum moments at a place that eliminates some of the other unknowns. So where would you like me to sum moments? B or C. So how about B? Let's do B. So we're going to sum moments at B. So what do we got? So we start at the left, work our way over. We don't need to consider the moment reaction from this. Don't need to consider the moment reaction from this. We do have 6,400 pounds generating moment. Is that going to generate positive or negative moment? According to my sign convention. Negative. Hold on. Here's B. 6,400 pounds rotating this way. Is that positive or negative? That's negative, right? Remember, you pick a sign convention and go with it. And what's my moment arm? Here, I'll erase that so it's a little clearer. What's my moment arm? 4. Right. Is everybody following along? Y'all kind of quiet this morning. If you got a question, don't hesitate. All right. You're not going to hurt my feelings. All right. What about this 2,000 pounds? Does that generate moment? Yep. Is that positive or negative? Negative. Mr. Hall's the only one answering questions, so I'm giving him a break. All right. Somebody help me out. What's the moment arm from B? 6. All right. Let's go to the next load. What about this 4,000 pounds? Does it generate moment? Yes. Positive or negative? Negative. Negative. Moment arm from B. There we go. I guess I'm going to have to drink this coffee I brought. Okay. Does the reaction at C generate moment? Positive or negative? There we go. Positive CY. And moment arm of? Boom. Now we're getting somewhere. So, let's see. So this is 12,000. This is 60,000. We'll say equals negative CY times 12. 64 times 4 was at 256. So 25,600. Did I do that right? So, okay. 12,000 and 60,000, that's 72,000. 72,000. 97,600. Somebody help me out. I'm just doing this in my head.
The final answer is 8,133.
Well, hold on. You skipped ahead. Say it again.
8,133.33.
So hold on. Well, let's do that. Do I have a second on that? Okay, all right. So, is this bringing it back? Y'all remembering this? Okay. So, now what do I do? Sum of forces in the y direction. So let me drag that down a little bit. So I got BY plus CY minus 6,400 pounds minus 2,000 pounds minus that equals 0. So BY plus 8133.33 pounds minus, what was that? 8,400, 12,400. What is that? Is that like 4266.67? Did I do that right? Help me out. How'd I do? Okay. Everybody's been a little quiet during this example, so I'm going to take a step back and go, does anybody have any questions about this? Is this bringing it back? Or don't hesitate if you got a question. So the 6,400 came from taking this distributed load and collapsing it into a point load. And so the beam is experiencing a 400 pound per foot load over a distance of a total of 4 plus 6 plus 6, 16 feet. So 400 times 16, that's the 6,400. So that's just me taking that distributed load and turning it into a point load to make it a little easier to deal with. Any other questions? Again, whenever you ask a question, chances are there's probably half the class is also interested in hearing the answer, so don't hesitate if you got a question. Sound good? Okay. Now, I sort of redrew the beam here. You do not have to do this. By redrawing it, I took the beam and I stretched it a little bit. I know that looks kind of gnarly, but I'm doing that because I want to make sure that we're all clear on what it looks like, and I didn't want to like cram it. So I know that looks kind of gnarly, but I think in the end it'll result in a more clean shear and moment diagram. Now, what I am going to do is I'm going to put these reactions here. This was 4266.67, and this one was 8133.33 pounds. But the big thing to keep in mind is when I'm drawing the shear and moment diagram, I'm drawing it for this. That 6,400 pounds that I placed on the beam, that was an arbitrary construct that I did to make the math a little easier. But that's not what's really going on the beam. The beam does not have 6,400 pounds lumped in one spot. It has 400 pounds per foot distributed over a length of 16 feet. Does that make sense? Okay. Now, if you remember when we did this in statics, one of the things that I suggested is that you draw some guidelines. All right? And what we're going to do is give us a nice reference point to start from. We'll say this is the shear diagram in pounds. Let me ask you this. You want me to give you a little bit to draw and get ready? I mean, I can wait a little bit because I don't want to. I see a couple people look like they're rushing, and I'd rather wait. I'll give you a minute to get caught up on this. Everybody good? Or do you need a little bit? Everybody good? Okay. All right. How does a shear diagram get constructed? You start at 0, and the idea is that you start at 0. That you will start at 0, and done correctly, you will end back at 0, right? So, let's see what happens. Let's go from A to B. What happens from A to B? See if y'all remember this. What type of load do you see from A to B? I mean, what's on the beam from A to B? All right, distributed load. Okay, how much total load is between A and B? It's 400 pounds per foot for a distance of what? 1,600. What direction are those arrows pointing? Down. Whenever you're drawing a shear diagram, you do what the beam tells you to do. I'm looking at the beam and it's saying, Greg, go down. So I'm going to go down, right? My first name's Greg. It's telling me, Greg, go down. We know each other. That's a joke, not a very funny one. Okay, so now we got everybody woken up a little bit. Okay, so we start at 0, we go down to 1,600. So here it's going to be 1,600. What is the shear diagram going to look like from here to here? A line going downward. So this is what the shear diagram looks like. Right here. Negative 1,600. Pop quiz. What's the slope of that line? You don't need to do any math. Negative 400. But you're right. The slope of the shear diagram is equal to the load. So that's negative, that slope of that line is negative 400. Now what's the beam telling me to do right here? Straight up. Now if I'm at negative 1,600 and I jump up 4266.67, what's that put me at? $2666.67. So maybe something about like that. Oh, something on my screen at that exact spot. It's a little convenient. And so a sudden jump. All right. Now, what happens from B to this point right right here. Maybe I should have put a letter here. Maybe we'll call this E. What happens from B to E? Well, how much does it go down? 400 pounds per foot for a distance of 6 feet. So 2,400. So if I'm at 2666.67 and I go down 2,400, what's that put me at?
266.67.
So scale-wise,
Real close to the line. The black line.
I think in 8 years of lecturing, that's the straightest line I think I've ever drawn.
Can you draw a circle now?
No.
I can't either.
All I know is Instagram that. That's all I know. Okay. I'm a dork. I know. Okay. So I'm at 266.67. Now what do I do?
Go down to the.
So if I'm at 266.67 and I drop down 2,000, what's that put me at? Huh? Did somebody? I didn't hear somebody say it. What was it?
Negative 1733.3.
There you go. So a little bit lower than that one. So when you're celebrating our exam 2, what do you think is a good idea to bring with you? There you go. And by the way, everybody in here should have a straight edge. Like everybody has a straight edge. So. Okay. 1733.33. Now what do I do from E to C? So what's that put me at?
Negative 31.33.
Is it negative 31? Is it negative 41?
Yeah, that.
See, I had to make a claim about that straight line because that one's. Ugh. All right, so if I'm at negative 4133.33 and I jump up 8133.33, what's that put me at? 4,000. So that's all the way up here. That is a big jump in shear, but that is a big reaction. Now what happens from C to D? So what do I draw? Straight horizontal line. A line with zero slope. Because there is zero load. And so I'm at 4,000. Drop back down to zero. Drop back down to zero.
There you go.
Zero. I need talking too.
I got a question.
Yes, sir.
So, on the perfect straight line, like your angle line from 2600 to 6612,
Yes.
what did you go to in the middle? Like the 266, I can't really see it, but like, is it the same number?
So this is 2666.67. This is 266.67. So if you take 2666 and subtract 2400, that's what you got. Yeah. So far, so good? Now, in order to construct the moment diagram, I need to integrate the shear diagram. So do I need to break out my little squiggly S integrals? No, these are triangles and rectangles, right? I can integrate a triangle and a rectangle because what does it mean to integrate? Determine the area under the curve. Let's start with this. Well, first off, did our shear diagram serve to verify our reactions? Partly, because we started at 0, and we ended at 0. Now let's look at this. Let's start with the simple area. What's the area under the curve right here? 4,000 tall, 3 wide. What is that, 12,000? All right. I'm increasing complexity, okay? So now we're going to look at this triangle between A and B. What is the area of this triangle? It's 1,600 times 4 over 2, because it's a triangle. BH over 2. So what is that? Negative 3,200? All right. Everybody pay attention up here. Y'all know how to compute the area of a trapezoid. So the area of a trapezoid like this, you take this number, and you average them. You average those numbers, multiply by the width. Or you could say it's a rectangle and a triangle, whichever you prefer. But I want somebody to tell me that total area. Because what we're doing is we're basically saying when you have a trapezoid, is we're saying we're going to compute the area of like that rectangle. And that rectangle has the same area as the trapezoid. So we just average the ends, multiply by the width. What do we get for that? It actually comes out to should come out to a nice round number because of the, you're multiplying by 6, so you have thirds. 8,800, do I have a second on that? All right. What about this last area? So this is 1733, 4133. And negative, right?
Yep.
Now I want to stop for a second. I want to make sure that everybody understands what we just did. Very good? You want to check to see whether or not these are correct. What is that plus that plus that plus that? 0. Why?
Because they all add up
What color is the wall? Green. Why? Because somebody painted it green.
to 0. That's correct.
Well, that's true. The reason that they are 0 is because we are integrating the shear diagram. Integrating the shear diagram yields the moment diagram. And the sum of moments are 0. There you go. Now, how to construct a moment diagram? Well, I'll be. All right. I'm going to give everybody a sec to draw this out, and then I want everybody to sort of pay attention to me. This is kind of important. All right. Everybody ready? Okay. Now, the first thing that we are going to do is we are going to determine the values on the moment diagram, then we'll determine the shape. So we are going to start at 0. Everybody watch me. So I got a lot of folks writing. I'm going to give you a sec because I want everybody to watch this. I'll give you time to construct it. Don't worry. I want everybody to pay attention to this. I'll give you a sec. We're not in any hurry. We got time. Everybody with me so far? Okay, look. So watch up here. This is what I'm going to do. I'm going to start at 0. And what this area tells me is that I'm going to go down to 3,200. So this right here is going to be negative 3,200. Now, if I'm at negative 3,200 and I jump up 8,800, what's that put me at right here? 5,600. So this right here is 5,600. Now, if I'm at 5,600 and I drop 17,600, what's that put me at?
Negative 12,000.
And if I'm at negative 12,000, I jump up, that puts me at 0. And before we start drawing anything, did everybody understand that? I've been teaching this class a long time, and I'm telling you, I can't tell you how many times students get here and they get lost because they're trying to figure out the littles to a lots or lots to a littles. Like, let's just start off agreeing with this. Okay? So far, so good? Now, let's start drawing the regions. Of these regions, 1, 2, 3, 4, which is the easiest to figure out? 4. Why? Constant shear, linear moment. This is going to be a linear moment diagram right here. That line wasn't bad. That one was better though. The rest takes some thought. So we're going to start here, work our way over. I want everybody to pay attention right here. Let's start. Everybody, eyes up. Okay, this one. Look at the shear diagram. In terms of magnitude, we go from a tiny amount of shear to a lot of shear. Right? Small amount of shear to a big amount. When we look at the slope of lines, right? This is a line with very little slope. This is a line with a lot of slope, right? So our moment diagram needs to go from a little slope to a lot of slope. The moment diagram in this region goes like this. All right. Now help me out with this next part. We go from a lot of shear to a little shear. So I'm going to go from a lot of slope to a little bit of slope. The moment diagram is going to go like that. Now, I'm actually going to use the chalkboard. For this last region, let's see if y'all's paying attention. How many vote option 1? How many vote option 2? Option 1 is correct. We go from small magnitude, large magnitude, bam. There's your moment diagram. So I should be designing this beam for a maximum positive bending moment of 5,600 foot-pounds, a maximum negative bending moment of 12,000. We'll talk a little bit later next week about, do we really need to consider both? Do we need to consider both positive and negative bending moments? There are some very clear instances where yes, we do. For example, if you have composite beams and you have different materials on the top and bottom of the beam, you might have to check both conditions because you have different stresses on the top and bottom. This is a very common instance in reinforced concrete design. In reinforced concrete design, we put steel where there is tension in the beam, right? So here, and we'll talk about this later, but here, tension is in the bottom of the beam. But over here, tension is in the top of the beam. So if this was a party deck, and I put rebar in the bottom over here, this would be a short party, because the beam would fail. So.
Yeah, very interesting.
breaking
That would not be a fun party. You and I have different definitions of what's fun.
Maybe for a split second.
It'd be like breaking
It
tape.
depends on the crowd, yeah.
Catastrophic death and failure has not been a fun,
You never said
the definition of a fun Saturday night thing.
It just makes it everybody's like,
Yeah, it's like, I'm a little concerned because we're doing these examples and whatnot, and everybody's like diligently following. But when we start talking about death, chaos, and destruction, everybody's like, oh, let's talk about that. I'm joking. It's a joke.
Adrenaline. We are in the business.
Oh, my Lord. All right. Let's talk a little bit about logistics, but before we do, I want to make sure this made sense. Anybody have any questions about this? The concepts? Everybody good? Okay. There is one other example that we didn't have time to complete. It's a cantilever beam. I'm not going to try and rush that in the next, 10 minutes. Instead, what I'm going to do is I'll probably just post a short little video going through that in the interest of also maybe letting y'all out, I don't know, a couple minutes early if you're okay with that. What we're going to do is starting Tuesday, we're going to formally start discussing bending theory and bending stresses and so on and so forth. So with that, you all have a wonderful weekend. I will see you on Tuesday.